So hello, everybody. First off, move down a little bit. First off, I'd like to say thank you, everybody, for being here. I can't say that 4 o'clock on Friday was my first choice of presentation time slot. Thank you, Steve. But I'm still very grateful to be here and very appreciative of this opportunity to be up here. My name is Will Stewart. I am the Industry Segment Manager for Data Centers with HARTING. I am up here with our Global Head of Product Management, amongst other titles, Andre Benica. And we are here to talk to you about a specification that we are developing through the OCP Rack and Power subgroup. It is a specification for an input power connector for the power shelf. So the agenda for today, I'm going to give a brief HARTING overview just to explain why I think we are the right company to develop this specification. I'm going to talk about the current power architecture in the Open Rack. I'm going to give an example of a company that implemented connectorization in their PDU to create a universal architecture, what benefits they saw from that, what benefits we think that will bring to the power shelf, and then we will unveil the concepts. And then we'll open the floor for questions. So to start off, a brief history of HARTING. HARTING was founded in 1945 by Mr. Wilhelm HARTING. 1945 was right after World War II. It was in Germany. Obviously, there was a lot of reconstruction going on in Germany, and Mr. HARTING wanted to do his part by creating small electronics for residential and maybe small industrial applications. But as he was creating these electronics, he realized that he didn't really love any of the connectivity solutions that were currently on the market. One of the options were something that I would call hardwiring, which is landing individual cables on a terminal block or on a PCB. But that limits your mobility, and you need a qualified electrician to be able to do it. It limits who can actually make that connection. The other option was circular connectors, which were a little bit better, but they're kind of difficult to use. You kind of just twist and don't really know when it's actually terminated. There's also density issues. If you're going to put a bunch of circular connectors on a panel, you can't just put them all together. You need to leave room for the hand, right, to be able to twist it. So we kind of looked at these, didn't really like the option, so he kind of thought that he wished that there was a rectangular connector. And so we invented it. Today, HARTING is approaching $1 billion in annual turnover. We have 13 manufacturing plants in North America, Europe, and Asia. We have about 5,000 employees. These are the 13 production plants. We have 44 sales subsidiaries. We are located in beautiful Espelkamp, Germany, about an hour west of Hanover. And we are still 100% owned by the HARTING family. We are currently led by the third generation, Mr. Philip HARTING, and his sister Marissa. And kind of beyond all this, I think HARTING takes a lot of pride in the fact that we are the market share leaders in a couple of important market segments, things like machinery, robotics, transportation. And really beyond that, why I think we got there is because we're the innovators in the connectivity market. I kind of shared the story of how the first rectangular connector got invented. Since then, we've invented things like modular connectors, the ability to put data, signal, and power into one connection. We also invented fiberglass reinforced plastic connectors. It's more cost efficient, saves weight as well. So really we like to be the innovators in the market. So when we heard that the Open Compute Project was looking for someone to take the lead on the development of a connection for an input power connector to the power shelf, we figured it had to be us. Okay, so now let's look at the Open Rack power architecture in V2, right? So power comes in through a busway, traditionally 12 volts, sounds like 48 volts is in the mix now too. But anyway, it terminates in a tap-off box with a small cable drop. That cable drop gets fed into the PDU, which sits on top of the rack, and then there is a cable and dongle which goes down into the power shelf. So right now, that connection between the PDU and the power shelf, you have a cable that has a proprietary connector. That's okay, but we are in the Open Compute Project right now, so we want something that is a specification, an OCP accepted product that's really open for anybody to develop and anybody to improve upon and release into the marketplace. I also think that it prevents the global architecture. I'm going to talk about this quite a bit in this presentation, but to kind of explain what I mean by global architecture, this is just an example of one hyperscale company of two different power architectures that they have in North America versus Europe. You can see that there's a difference in amperage, there's a difference in the wire gauge, there's a difference in the plug, and this really prevents people from using one rack architecture everywhere. This is just one example that I have up here. You can also have different permutations in the regions. And things like, I mean, you can go down to 12 amps, up to 50 amps. You can have higher wire gauges. You can have a California standard plug, things like that. So why is a global architecture important? In order to explain this, I'm going to give an example of a company that is a part of the Open Compute project that implemented connectorization on their rack PDU. That company is Microsoft. This is Project Olympus. So what Microsoft did is they switched from what I would call a hardwired rack PDU, which is when the cable goes into the rack PDU, lands on terminal blocks, there's a cable grip, and you can't really separate them easily, right? You need to actually break it apart. And they switched to a connectorized PDU. So you can see a couple examples over here, right? With the connector on the PDU. This is our bulkhead on the PDU. This is the cable that goes into it. So why? So why did they do this? I think what Microsoft noticed when they looked at their forecasting and looked at their supply chain is that, well, let's put it this way. Anybody who's in the data center industry, I think, knows that you don't know what you need until you need it. And when you need hundreds of them, and you need them now. So Microsoft looked at their rack architectures, and they realized there was about 5 different rack PDUs that they were using, right? They had different power levels. They had different amperages, 12 amps to 50 amps. And the most important part is each one of these had a 6 to 8 week lead time. Well, when they wanted to build a data center, they couldn't wait, or expand a data center, replace a data center. They couldn't wait 6 to 8 weeks. So they said, how do we get around this lead time? And they said, well, I guess what we could do is we could just order a bunch of all of these different power architectures that we have. We can have a stock, and then whenever we build the data center, we can just use out of that stock. The problem is, if you have 5 different rack PDUs, you're only using 20% of what you're stocking. There's a bunch of liability in your supply chain. So that wasn't really a great option. So what they said is, well, what if we redesign our rack PDU, create one rack PDU that can be used in every single, different orientation, and then just have the cable be different, right? The cable can represent the power architecture, can have the right, plug at the end, and then you can just plug it up once you're actually at the data center. So they gave us a call. They gave HARTING a call and said, this is something that we're trying to do. Can you help us design this? We said, sure. We were able to drop the lead time from about 6 to 8 weeks from the rack PDU to 2 weeks for the rack PDU. And this is worst case lead time. Often usually Microsoft has stock already. So you could say, okay, well, that's good. You had a decrease in the supply chain. You limited your liability in your supply chain, but you still need to factor in that the connector is more cost, right? You need to have a cost comparison of, is it worth it to implement the connector, and is that worth having a simpler supply chain? Well, first off, I'm going to tell you the answer is yes, but I'm also going to tell you that the answer doesn't matter. Because whenever you refresh your data hall, that power cable that you normally had to throw out when you ripped and replaced racks stays there now. That power cable costs more than the connector. So you're actually saving money over the lifetime of the rack, of the lifetime of the data center, by implementing the connector. Simplifies supply chain, optimize inventory, I've kind of already talked about. So this is what we're proposing for the V3, PowerShelf V3. You get rid of the PDU. I'm not really an expert on this, but the PDU electronics can be placed into the PowerShelf. Have a cable drop that goes down from the tap-off box of the bus bar directly into the PowerShelf. It'll streamline, simplify the design, create one less point of failure in the PDU. And through this, if designed correctly, Steve's job, is to, you can create one rack architecture that can be used globally and create an inventory that can be deployed immediately. But we need a connector that can handle this. And the connector that can handle this, it's actually not that difficult of a connector, right? 50 amps isn't that big of a deal. The wire gauges, 10 gauge isn't that big of a deal. It's the size that's tricky. We'll go into that a little bit later. So benefits, I'm going to be honest, I've already gone through all these. I just know this presentation is going to be published, and so I just wanted one slide that says all of them. But one rack design used internationally, reduced liability and inventory, fewer SKUs, faster deployment, retain the cable hauls during the data hall refresh, retain cables during data hall refresh, and decrease total cost of ownership. So what do we need now? An input connector that can handle all the power and dimensional requirements. I would say we need an industry-proven technology leader to innovate and partner for OCP standardization. I gave an example of partnering with Microsoft in order to create the universal PDU. On top of that, we're actually with 3 other hyperscale manufacturer or hyperscale data centers as well, using things like our Han Eco on their rack PDUs and in their remote power panels, or using our Han docking frame blind mating solution to create for the blind mating for things like maintenance bypass, the BBUs, things like that. And we need to create an OCP specification and put an OCP accepted product in the marketplace. So who do you think we should do? Who should be able to create this? I was going to say one of our competitors here as a joke, but I don't think that my management would like it. No, it's HARTING. So now I'm going to pass it over to Andre to unveil it.
Thanks so much, Will. Yeah, like he already said, one of the key requirements for this new connector concept has been the space. So the connector should be as small as possible. At the same time, it should be able to transmit as much power as possible. And in the end, that led to the following design proposal here. You can see the overall space restrictions, which were defined before, and the connector design, which we have now created, basically matches those space requirements. Actually, it's even a little bit smaller than the maximum dimensions which were defined before. Going a little more into details regarding the connector itself. Even though today the power requirements are lower, we clearly said we want to be future proven. That means regarding the currents, we wanted to go up to 50 amps max to be totally future proven. That's what this connector design fulfills. Even though today we will most likely be looking at 20 amps or 32 amps, normal use. So the wire gauges which can be terminated go all the way up to gauge 7. But of course also here, normally we're talking about gauge 10 wires for the 32 amps. So in case in the future the power requirements are increasing, we are pretty safe there. Maybe to go one slide back again. Another topic was we wanted to be able to put up to 4 connectors onto each of those power shelves. So that means 2 of them can be placed next to one another on one side of the bus bar and another 2 on the other side of the bus bar. That's also the reason for those angles we decided to propose for the cable entry, just to make sure that that 2 connectors can be placed as close as possible to one another. The locking mechanism is realized with the help of 2 latches here at the side. You can see it here and also there. So basically you just need like 2 fingers to press them together, and then you can unplug. And when you plug the connector in, it automatically clicks in. Another point which we believe is important is that it should also be visible if the connector is correctly locked. So we have made a design which indicates, just by looking at the surrounding material, if the latch is still slightly open or not. So that means there's also an optical verification existing that the connector is properly mated. Overall, well, that's what I mean with positive latch here. Overall, the connector is coded. So depending on the position of the connector in relation to the bus bar, it's always 180 degrees coded. Plus, if necessary in the future, an additional optional coding is implemented as well. The contacts are finger protected. potentially on both sides, so male side as well as female side are finger protected, which is a nice benefit from my perspective. Just increasing the safety for the user in the end. To give you a little bit of an idea regarding the overall size, because one thing is looking at it on a PowerPoint slide, the other thing is looking at it in real life. I got one sample here with me. This is obviously a 3D printed sample. So after the presentation, of course, we are here for discussions. So you're more than welcome to come to us and have a look. That's clear. So pretty small, pretty compact, and at the same time made out of as few components as possible. Because in the end, we're always talking about costs. So the connector has to be inexpensive, and this is only possible if we use as few components as possible. So that means when you look at the injection molding parts which are needed, very small number. Also the contacts, standard contacts in the end. So everything is really designed to cost. Looking at the possible timeline, because at the moment, 3D printed samples, we still are in the conceptual phase, and that's also part of the reason why we are here today. We wanted to discuss with you, get your feedback on this proposal, to make sure that everything which could come up as future requirement is implemented into this, this design here. So hopefully we will get a positive feedback here and today. Then we believe that within the second quarter of this year, we can basically finalize everything regarding the specification behind, make the additional necessary presentations. In Q3, the idea is to have the final discussions with the incubation committee and also manufacture real samples then, which can be used for tests. And prospectively, until the end of the year, we should be ready for serious production. So that's the rough timeline we have in mind. And this young gentleman you've seen before, of course, we need somebody who's always there to be contacted with regards to questions or whatever. Of course, today I'm here as well. And that already brings me to Will now. No final words from your side?
That's it. No, I just wanted to show him.
OK, we are very good at time, actually.
Pretty good.
So thanks for your attention, and we are open for questions now.
Yeah, my questions are on UL listing. Okay, so the idea is, when do you, is the product designed to be UL listed?
For sure.
And when will the UL listing be available?
Normally, you go into the UL approval process with first parts out of tools. Depending on how fast they are working, this usually takes up to 4 months to get the final approval. So my assumption is we will not have the UL approval by end of this year. It will probably be first quarter of next year.
Okay. Other questions are, does ground mate first?
Yes, the ground pin is the middle one, and that mates first and breaks last.
Okay, and we have...
And maybe one addition, it's also independent of the mating angle. So we've designed it with as much pre-leading as necessary.
Okay, and we have applications where there's a 3-wire, 3-phase, 480-volt shelf specification. Is it designed to support that?
Yes.
Well? Okay.
It's for AC as well as for DC.
Okay.
Mm-hmm.
Thank you.
Any further questions?
Question, how many number of life cycles do you expect? Is
How,
it like
how many? I'm sorry?
hot swap, hot plug, I mean.
Okay. You mean under load?
Yes, I think for UL 1682 and 2682, they required, I believe, 2,000 cycles.
The connector itself, is not like an IEC or a NEMA plug, which is by the design designed for, let's say, disconnecting under load until the maximum number of mating cycles which are specified. So that means this one will be designed to be mated and unmated without load. But of course, in case that happens, it can withstand a certain number of mating cycles. I believe the UL specification requires 50 mating cycles, if I'm correctly informed. And this will be covered by this connector.
So you say the connector doesn't technically support the live plug and unplug. But then how you control this under the data center? Maybe the technician can take them out and plug them in while they're live.
Well, normally when you look at the plugs, and I believe that's also true for the plugs which are used today. I'm sorry?
Yes, it's more of the hot swap or the total reliability of no, the live, it's just hot swap. Yeah.
So you're talking about disconnect under load?
Yeah, under load.
Yeah, that's what I'm referring to. So the connector withstands disconnecting cycles under load, but it's not designed for a continuous operation like that. So when you think about one of those big circular plugs, right? An IC or NEMA plug. So there's a specific reason for the size of those connectors. Because they are really designed for being disconnected under load for like 1,000 times. And when you make smaller connectors, like the ones which are used on the drawer units, on the shelves, those are normally designed not for disconnection under load, but of course you have to make sure that if that happens, that the connector can withstand that. And that's true for this design as well. So the connector can withstand it, but it's not really intended to be used like that.
Mm-hmm. It's kind of, it might be difficult on the fleet-wide to avoid this situation. It might happen, and then as a result, then the resistance of the contact might increase and may cause to catastrophic failure. Over time.
Maybe to give you another example. When you think about those rack PDUs, you always got those 3-pin connector plugs in there to go to the different units, right? So this 3-pin connector is also not one of those which should be disconnected under load. Same thing.
Yeah, I got you.
That's the reason why it's so small.
Okay.
Can I answer?
Sure.
Actually, for the kind of hot swap, there is a standard UL 1977 test, which is 250 volt with 50 couplings. But this current is specified current, what current we test. So that what like he's saying that it is not intended to be like that, but if it is happened, the UL 1977 test, if you meet the test, then it will be fine.
Exactly.
Is that okay? My question is, go back to the design.
Go back to the design?
The design, the new design.
It's easy to do this.
Okay, the cable side is it's a crimp, right? It's a crimp termination, right?
Correct.
And how does the strain relief work on the hood?
The design is made in a way that the black material which you see there is an overmolded material. So it's basically filled with rubber material.
Okay.
Can I have the laser pointer?
Yeah, of course.
So the surrounding material, obviously, that will be plastic, as we plan at the moment, most likely polyamide. And the black material here is basically like potted material. It's
a potting. You have to pot the material, or
correct.
Or you insert mold. I mean, you
overmold
it.
We insert mold.
So you it's overmolding cable assembly.
Correct. In the end, again, for cost reasons.
So the hood is a single piece.
Correct.
It's not a 2-piece.
Correct.
Okay.
One question interesting, maybe not addressed to you directly, for people who is present in community, and that about new project related to vSwitch Power Shelf. Of course, one of the super important story, this is a cost, yeah. And try to imagine it, how many time per life of the Power Shelf we can disconnect him from the up-level bus bar, for example, from data center bus bar. I think the 2 or 3 maximum times. And the question is everything about cost. Why we can use standard ceiling, screw ceiling, use it in any standard IP65, for example, box or rack ceiling, just for keep a cable connected to the terminal box and screwed or any type of connected to terminal box inside and power distribute to power shelf. Why we need to have a connectors? What's the reason for?
Sure. So from Facebook's standpoint, right, and this, you kind of alluded to this as well, right? If it's a direct wire interconnect to the back of the power shelf, then it normally would require an electrician to make that interconnect, as opposed to just a lesser trained technician that's building this. We don't have to have a certified electrician do that hardwiring. So that would have to occur in the data center, right? We'd have to have a data center technician, at least for us, right? If we have the rack that gets deployed, it gets delivered with just terminal blocks, right? Those wires would have to be terminated by an electrician. Instead of just the guy that's rolling the rack into position, he can just take the cable and plug it in because it's connectorized like this. So that's the value of the connector, is you don't have to have a certified, licensed electrician put those wires in.
And maybe to add to the point, I would say the key benefit is really, first of all, in the production process of the individual components, because obviously the power shelves need to be tested before being installed in the end. So you can optimize the testing process if you have a connector. Then installation, like Steve explained, that's another benefit. And if something goes wrong in the data center, if you got a failure in one of the systems, you can easily disconnect and replace units. So you're right, the connector normally in these applications is made it like 3-4 times during the lifetime of the connector. Maybe to give you a kind of comparison where this is also done in a very similar way. When you look at cars, in a car today, well, HARTING is not really the key player in that industry, but the competitors being in here will probably agree. There are like 1,000, 1,500 connectors in every conventional car at the moment. And most of them, I would say 99% of them, will be plugged twice, during production and during assembly of the car. That's it. But the value of the connector use in there is really in the whole logistics process behind.
Yeah, you easy to. I easily understand you if I be there on your side. Mm-hmm. Because and finally, in any car, you and me pay for hundreds of connectors. Use it only 2 times in a life.
Well, if your process costs during the production of the car are therefore cheaper, the customer benefits as well.
Customer the same for the car and for any B2C device, but this is absolutely different story, not possible to compare with the car, because complexity of the power shelf, it's absolutely different than complexity of the car, especially for many things. We can talk about that. Yeah, in a question, it's clear and understand it, but EEC connector with 32 amps, for example, standardized. It's maybe is okay for that. Okay, it's I understand your opinion about that.
Yeah, I mean, if the cost of that connector is relatively modest compared to having that kind of a skilled technician do those kind of interconnects for us. So that's kind of what drives it.
Okay. Another question?
Yeah, I just want to make sure I understand how this all goes together. So you're crimping, and then you're installing, and then overmolding. And then overmolding is providing the contact retention?
No, the contact retention is basically done by the plastic material because the contacts are pressed into the plastic.
Oh, all right, okay.
Yeah.
Clip in.
Gotcha. And then for the overmolding material, what material did you have in mind for that?
We have not finally chosen that yet.
TBD.
Okay. Okay, thank you.
Go ahead.
Sorry. And then the contacts, is it just a screw machine pin and a stamped to form socket?
Those contacts in the mating area here will be machined ones.
Okay.
But in the end, depending on the further players joining this game, of course, they can also be stamped and formed.
Okay.
So that's not going to be like part of the specification. Yeah.
So I understand the value of having the connector there for the same reason that Steve mentioned. But I don't understand the value since this connector doesn't have the under load connect and disconnect. So how is the normal process would be? So the rack lands at that location, probably with the servers and all the machines in. Probably cannot plug it in. We need to take out the machines and then plug in, and then we take the machines in again. Take the machines out, plug in, take the machines in again, and the same process when we want to take it out. Yeah?
No, the first interconnect, right, would probably not be under load from the IT gear, but it's you'll still have the load from from main power. So I mean, to your point, right? I mean, it's gonna be cycled those 2 or 3 times. It probably almost invariably it'll be under load, right? It won't be very many cycles, but it will be under load.
But I mean, those are conditions that you don't want to happen. But in a normal process, you have to follow these steps. Land the rack, plug all the trays, plug in.
No. Yeah, it's all interconnected.
If you have 480 volts though, with 30 amps, you put a plug there, it's going to be a spectacular event.
Yeah.
The power supply is going to be turned off.
Yeah.
When you go around the back to unplug it. So why would there be a load on there?
You'll know.
Well, if the power supply is turned off.
But if you don't, turn it off, you'll know it.
This is what the worst case, unexpected. Not on the everyday stuff. Sometimes.
So the whole rack is live and you can pull the plug.
Well, that would be one of those unexpected conditions, right?
Yeah, we wouldn't recommend it.
Normally,
wouldn't
it would be,
recommend
right?
it.
Yeah. Right. I mean, you've got the controller inside the power shelf, right? That would regulate that power. So.
Yeah, but that is very difficult to unplug. This one's going to be very easy.
This is one of the points.
At 480 volt, that's going to be spectacular. Because you could draw hell current at 480 volts.
I mean,
I think also, Ed, you have a question over here too.
yeah, we got another one.
Yeah. Okay. I didn't come as prepared as you came prepared, so I'm not sure if what I'm saying is exactly true. But the idea is that this will be connected by a branch circuit. So there's going to be a circuit breaker typically feeding the wire.
I
And
mean, in the tap-off box?
yeah.
Yeah.
Okay. And I have some vague memory of DIN breakers being 63 amps being a really common number. And so my understanding is that when you have a branch circuit, the stuff downstream that it's feeding needs to be able to support the breaker rating that you use. Now, I don't know what temperature it needs to be supported. So maybe, it's 50 amps at the real operating temperature, and it's 65 amps at 25C or something. But my understanding is that if I've got a breaker that says 63, I can run maybe 8-gauge wires down to it. But my expectation is that everything protected by that 63 amp breaker will support 63 amps. So that could be, that could be wrong, because again, I didn't come prepared. But I'm used to sizing that branch to support the nameplate breaker rating. And so that's a by the way, please look at that. Okay, thank you.
Yeah. So it's 63 amp breaker, but we're calling this a 50 amp. I mean, I think the 50 amp is nominal use. I'm not saying it's, it can't support up to 63. We have to look at that. It's a good point, and we'll look into it. Thank you.
I just want to be able to put it in a branch circuit with a DN 63 amp.
Yeah. We'll look into that. Thank you. All right, anybody else? Sure.
Sure.
What is the current rating? What is the temperature rise for the 50 amps?
For the 50 amps,
Expected?
we have just finalized the according simulations on that. The temperature rise is somewhere around 50 degrees C.
50 degrees C.
Yes.
So it's not CUL, it's more than CUL. CUL is 30 degree rise.
Correct.
So it's 50 degree rise.
With the 32 amps, we are somewhere around 20 degrees C temperature rise.
Okay. What's the initial contact resistance? Contact resistance for individual contact resistance. Have you done any, power loss calculation and all based on the contact resistance?
Yes, we have done that, but I
Okay.
don't remember those by heart.
Okay.
So I would be forced to supply them afterwards.
Okay.
But in the end, they are in line with our normal resistances of the contact systems which we have. And if I remember it again, well, somewhere around 0.5 milliohms, somewhere around that.
Okay. Okay, thank you.
Any further questions?
Okay, so high performance contacts are sometimes louvered, in that they've got a lot of contact points. Are the contacts in this connector, are they louvered?
What does that mean?
A lot of ribbons that go. So like if
You mean like many contact points?
yeah.
Yes.
Okay, so they're already there.
Yeah, as I said, the design which we've made is based on turn contacts, and it's like a tulip design on the female side
Yeah.
with like different, let me call them leaves,
Yeah.
touching the male contact.
Okay, and I guess the question is there a more expensive contact technology that could be used with perhaps a plastic key, so that you could have a family with more ampacity that lived above this one, but higher tech on the contacts? I'm not looking
Theoretically, yes, but in the end, from my perspective, the limitation of the connector is then also defined by the cables which you can terminate. So obviously, mechanical-wise, you're reaching a certain limit then, and if you're talking about gauge 7 wires, well, you know what the current ratings are, so that's the limit in the end.
Cool.
Okay.
And then I also want to say that we also have some giveaways, some goodies. If you guys didn't get enough swag so far, thank you guys. Really appreciate the time up here, and yeah, my contact information's up there. If you have any questions, feel free to reach out.
Okay, thanks for spending the time.